Hello, everyone. You've probably noticed as we've been working through these videos that the various statistical tests that we've talked about each has their own set of assumptions associated with them. What we want to talk about today is what happens when those assumptions are violated. Now, if you recall, oftentimes we can't measure everything in a population, and so instead we measure a subset of the entities in what's called a statistical sample. Now, when we perform statistics, we're actually doing two separate things. The first is to provide an estimate of the population. So in this case, we might be estimating the abundance of sea otters on the California coast. But the second aspect of statistics has to do with inference, about drawing some conclusions about what the true population status is. And so statistics always have these two components, estimation and inference. And each of these components has different assumptions associated with it. If we want to get unbiased estimates of a population mean or variance, let's say, then we need to make sure that each entity within the population has an equal probability of being included in our statistical sample. And this is what I mean by collecting a random sample. Now, if you recall from our sampling designs, we can achieve this goal using other sampling designs like systematic sampling or a stratified random sampling design. But I'm using the term random in this case as a bit of a shorthand to simply represent that each entity within our population has the same chance of being included within the sample. In addition, we need to make sure that each observation in our sample is independent. That is, that the inclusion of one observation within our sample doesn't make any other entity more or less likely to be also included in the sample. And so these aspects of randomness and independence in our sampling is important for getting unbiased estimates of our population parameters. Now, when we want to go to the next stage and then draw some inferences about our population, usually in terms of calculating a p-value, then we oftentimes need to also meet some assumptions about the underlying distributions that we're going to use to calculate that p-value. Now, there are a variety of different statistical tests that we've talked about so far in these videos. And if you recall, this assumption that our sample is a random representation of the population and that observations are independent was characteristic of each of the statistical tests that we've talked about so far. But then once we draw inferences from some assumed underlying distribution, we need to apply some new assumptions. So for example, when we use the chi-squared distribution for our goodness of fit test and our contingency test, we also made the assumption that the expected frequencies in any one cell were not too low. And if you don't recall the details of these assumptions, I'd refer you back to the videos on those subjects. But now that we've moved a little bit deeper and started to talk about the t-test, either as a one sample t-test or a two sample t-test, we had some new assumptions that came to bear. The first is that the data are normally distributed, and in the case of a two sample test, that the variances in the two samples are equal to one another. So why do distributions then have assumptions in the first place? Well, remember that we use distributions to draw inferences given uncertainty. And distributions work because most of the time when we have data that are kind of like this, our test statistic will follow a very predictable pattern that we can describe mathematically as a distribution and use this mathematical relationship then to calculate a p-value. But if we want this distribution to work for our data, then it's important for our data to look like the types of data that are appropriate for this particular distribution. And these assumptions then define the key ways in which our data must be like this particular distribution in order for the p-value to be correct. So unbiased estimates then depend on random and independent observations, while appropriate inferences depend on how well our data match the distribution that we're using to calculate our p-values. So how do we assess then whether or not the assumptions of our statistical test are being met? Well, in some cases, this is really straightforward, but in other cases, it's not so obvious. And those are some of the things that we'll spend most of our time talking about today. If you recall, as an example, the goodness of fit test, where one of our assumptions was that none of the frequencies of expected values in any of the categories could be too small. In particular, the goodness of fit test assumes that none of the categories have expected frequencies less than 1, and no more than 20% of the categories have expected frequencies less than 5. Well, in this case, it's a very easy assumption to determine whether or not it's met, because we calculate the expected frequencies and we can simply look at them to see whether any of them are less than 1 and whether 20% of them are less than 5. So in the example of the birth dates of NHL hockey players, we can see that all of the expected frequencies in this example are very large, and so the assumptions in this particular case are all met. But in other cases, it's not so immediately obvious whether the assumptions of our statistical test have been met. If you take, for example, the two-sample t-test, we have these additional assumptions that, first of all, the variances are equal between the two samples, and that the observations are normally distributed. So in this example that we worked through in the two-sample t-test, where we had the fecal cortisol metabolite levels of control squirrels and squirrels tricked into thinking they lived in a high-density environment, we have two different samples with observations that are distributed something like this. Now, when we look at these histograms, it's not immediately obvious whether or not these observations are normally distributed and whether or not the variances in these two samples are equal to one another. So this is a situation where our assessment of whether or not the assumptions have been met is going to require a little bit more of a sophisticated approach and a little bit more of a subjective assessment. So let's first take a look at this assumption about whether or not the variances in our two samples are equal. First of all, it's important to note that this assumption only applies when we're comparing two samples to one another and doesn't apply to a one-sample t-test. Now, one of the objective assessments that we can make about these variances is a test called a Levene's test that objectively determines whether or not the variances in our two samples are equal. Now, it's important to remember that in this Levene test, our null hypothesis is that the variances are equal to one another. And we only reject this null hypothesis and conclude that the variances are different if they are sufficiently large to get a p-value less than 0.05. So we can use some code in R then from the CAR package and this Levene test function to determine whether or not the variances in our two treatment groups for fecal cortisol metabolites is in fact different. And what we found from this Levene's test then is that the p-value was greater than 0.05, and so we do not reject our null hypothesis that the variances are equal. So this Levene's test then could tell us that we met this assumption of equal variances and that we can proceed with our two-sample t-test. Well, what if the variances aren't in fact equal? Well, even if variances aren't equal, If the sample sizes are large and equal in the two samples, then even pretty big differences in variances actually aren't much of a problem for these two sample t-tests. If the variances were in fact quite different, we might instead choose to use what's called a Welch's t-test, which doesn't assume that the variances are equal between the two samples. We can use our same notation in our R code for our t-test as we did before, but in this case, all we need to do is specify that we are no longer assuming that the variances are equal, and what we get out is a Welch's two-sample t-test that gives us our t-test statistic, our degrees of freedom, and our p-value. So let's move on then to our second assumption about the observations in each of these samples being normally distributed. So how can we assess then whether the data in our sample are normally distributed? Well, there are three different ways that we can do this. The first is probably the most familiar to you, and that is by visualizing the data in a histogram. Another way that we can visualize the data to assess normality is using what are called quantile plots. And finally, a Shapiro-Wilk test provides us with a formal test of normality for our observed sample. So you've already seen histograms of normally distributed data. Here is an example of a distribution of body temperatures in degrees Fahrenheit. And you can see by looking at this histogram that it has all of the characteristics of a normal distribution. We have a symmetrical distribution where the most frequent observations fall in the intermediate range of the distribution, and it has this characteristic bell-like shape. In contrast, here are four other distributions that are very not normally distributed. Three of these distributions are very skewed either to the right or to the left. And this bottom right distribution looks relatively symmetrical, except that there's one outlying observation that we might refer to as an outlier. Now, outliers are normally defined as being observations that are more than 2 standard deviations away from the mean. So these are situations where it's fairly obvious from visualizing the histogram that the data are not normally distributed. But in many cases, it's not so obvious. If we look at these 8 different histograms, they don't particularly look like the characteristic bell-like shape of our normal distribution that we see in many examples. But these are, in fact, random samples from normal distributions that have the same mean and the same standard deviation. The top 4 samples were drawn with a sample size of 10, and the bottom 4 samples had a sample size of 20. And so these all came from normally distributed populations, but they don't look particularly normal. Another tool that we can use to visualize our data and assess whether or not they are normally distributed is what's called a quantile plot. In a quantile plot, we simply plot our observations against the theoretical observations or the theoretical expectations of what we would expect for each observation if they were in fact normally distributed following our standard normal distribution with a mean of 0 and a standard deviation of 1. And so if our observations are normally distributed, we expect the dots to fall along this straight line. Now these QQ plots can be a little bit tricky to interpret. We expect the observations to fall along the straight line, but how far away do the dots have to be from the line before we conclude that the data are no longer normally distributed? Now, I've looked at a lot of these plots in my career, and most of the time, even with very normally distributed data, you do get these wobbles where the dots fall off the lines. But there are some characteristic patterns in the dots falling away from the lines that can be indicative of other types of distributions. To give you some practice in interpreting these QQ plots, I've just created 4 different samples that have different distributions. The first sample is our typical normal distribution. This sample is skewed to the right. This sample is leptokurtic. And what I mean by leptokurtic is that the tails of the distribution are too fat. It no longer has this characteristic bell-like shape. Now, the opposite of leptokurtic is referred to as platykurtic, and that is a distribution that's tails are too small. Too many of the observations are clustered in and around the mean. So in the top row then, we've got the histograms that you might be more familiar with looking at. And in the bottom row, I've plotted the same data using our QQ plot that might be less familiar to you. And so you can see, first of all, in the left-hand panel, that when our data are normally distributed, the dots or observations fall pretty evenly along this straight line. And the situation for our right-skewed distribution is quite different. Here we have the line of expected values right here, and for some of the distribution, the observations fall right along the theoretical expectation. But the biggest departure then from what we'd expect occurs down here, where our smaller observations are not nearly small enough compared to what we would expect. They're too big. Okay. In terms of our distribution that is leptokurtic or too uniform or not peaked enough, we can see that the small observations are not small enough and the large observations are not big enough. So we have the data points falling above the line at low values and below the line at high values. In terms of the platykurtic distribution, the situation is entirely the opposite. Our small values are far too small, they're falling below the line, and our large values in our sample are too large. And so we've got way too many extreme observations at the tails. So these are just 4 different examples of ways in which our distributions might deviate from normality and how those histograms for those samples corresponds to this QQ plot that you might be less familiar at interpreting. Now, there is some nuance to looking at these visualizations to try and assess whether or not our observations deviate from a normal distribution. And so it's not uncommon to want some sort of objective test that will tell us, are our data normally distributed or not? And there is such a test called a Shapiro-Wilk test that provides us with a formal statistical test of how well our data fit the expectations of a normal distribution. And just like our Levene test for our equality of variances, the Shapiro-Wilk test has a null hypothesis that the data meet the assumption. And so we only conclude that the data deviate from the assumptions if this null hypothesis is rejected and the p-value is very small. But because this is a statistical test, we have to be really careful about how power plays into our ability to detect deviations from normality. If you have a very large data set, you have a lot of power to be able to detect even very small deviations from a normal distribution. In contrast, if you have a really small data set, you have very little power to be able to determine whether or not your data set deviates from a normal distribution. And so as a result of this, I worry a bit about objective tests like this, because I think they give people a false sense of security, kind of abdicating responsibility for this conclusion to this statistical test to tell me whether or not my data are normally distributed, without really pausing to look to see how are they deviating from normality. Is this a big deal or is it not? And as a result, I prefer to use the visualizations as assessments of whether or not the data deviate from normality rather than a formal statistical test like a Shapiro-Wilk test. So regardless of how you assess the normality of your data, what should you do if your data aren't normally distributed? Well, there are really three options. The first is to ignore this violation of the assumptions. The second might be to transform your data to try and make them normally distributed. And finally, we might abandon our statistical test and perform a different statistical test. Now, this first option of ignoring this violation of our assumption sounds irresponsible at first, but it turns out that a lot of statistical tests are fairly robust to violation of this assumption. And what I mean by robust is that even if this assumption is violated, our p-values are actually pretty close to what they ought to be, unless there are really severe violations of this assumption of normality. In addition, it's important to remember that the p-value that we're calculating corresponds not to the distribution of the data, but to the distribution of sample means. And if you recall that if our data are normal, then our sample means will be normally distributed. But even if our data aren't normally distributed, those sample means might themselves be normally distributed as a result of the central limit theorem if our sample size is fairly large. The second thing that we might do if we find that our data are not normally distributed is to transform our data. What a transformation is a mathematical function that we apply to all of the observations in our sample. Now, these typically aren't linear transformations, and what I mean by this is adding a constant or multiplying or dividing by a constant. Because these sorts of linear transformations don't change anything about the distribution of the data other than perhaps shifting it to the left or shifting it to the right. The shape of the data, the shape of the distribution is unaffected by these sorts of linear transformations. Instead, the transformations that we typically apply to try and deal with some of these assumptions of our models are usually designed to keep the rank order of the observations the same, but to change the variance in the sample. And so in some ways, what we're doing by these transformations is to simply change the scale on which our measurements are taken. So let's take, for example, this sample of very right-skewed data, where we have a lot of small observations and a small number of really large observations off in the right tail of the distribution. So here we have this very right-skewed distribution, and we can see then that our large observations are way larger than we expect them to be based on a normal distribution. But we can transform this distribution using a log transformation, in this case, log to the base e, or the natural logarithm. And we can create or get a new distribution of the same data where each observation has simply been log transformed. And we can see that on this log scale, the observations are in fact very normally distributed. So here we took a very skewed distribution, transformed it using a log transformation where the new observations are equal to the logarithm of the original observations. And we get ourselves a nice normal distribution that will then meet the assumptions of our statistical test. Now, a log transformation is probably one of the most common transformations because they tend to work well for observations that result from multiplicative processes. And these tend to have very skewed to the right distributions where the mean and variance are positively correlated. Now, in other situations where we have count data, a square root transformation might be more appropriate. When we have proportions, they're typically not normally distributed when the mean is far away from 0.5 and gets close to a proportion of 0 or 1. And in this case, an arcsine square root transformation seems to work well to normalize the data. And the final type of transformation that I'll mention here is a transformation that's appropriate for time to event data, how long it takes for something to happen. So how long it takes for an animal to die, or how long it takes to complete a task. And with this sort of time to event data, an inverse or reciprocal transformation where we take 1 divided by our original observations to get our new transformed variable tends to work well for normalizing these types of data. So instead of ignoring the fact that we violated an assumption or transforming our data to meet the assumption, we can also abandon our statistical test and employ a new type of statistical test. Now, most of the statistical tests that we'll talk about in this course are what are called parametric tests that rely on distributions. But there are a set of statistical tests referred to as non-parametric tests that are typically based on ranks of observations rather than their magnitudes. And as a result, these non-parametric tests tend to have less assumptions associated with them. But because they throw out some of the information contained in the sample and reduce all of those measurements of magnitudes down to simply their ranks, these sorts of non-parametric statistical tests tend to have less power. And we're not actually going to spend a lot of time on non-parametric tests in these videos because there are oftentimes better ways and more powerful ways to deal with some of the problems in the data that we might encounter. An alternative framework from non-parametric tests that we might use to calculate a p-value are what are called permutation tests. So if you recall, the reason we use distributions is to be able to calculate a p-value. And when the assumptions are met, the test statistic will follow a known distribution that allows us to calculate an appropriate p-value. But instead of using these theoretical distributions, a permutation test creates our own sampling distribution. And we use this empirical distribution to calculate a p-value that doesn't assume any underlying distribution. So how does this work? Well, the basics of a permutation test involves 3 steps. The first is to take our data and measure some test statistic or measurement that we're interested in with the data. Next, we permute the data, or we randomly shuffle the data so that we're reorganizing it in a way that breaks the hypothesized connections in the data. And once we've reshuffled the data, we recalculate our test statistic. And if we do this many, many times, we now get a distribution of test statistics from our own data that we can then use as our null sampling distribution. And once we have this sampling distribution, we can simply calculate the p-value as the proportion of permuted test statistics that are as extreme or more extreme than our measured test statistic. So very similar philosophy to our use of distributions, but instead of using a theoretical distribution, we're creating our own empirical distribution of test statistics by randomly reshuffling the data. Now, it might be a little bit hard to follow what I mean by that, so let's work through an example. So here we have the data for our experiment where we exposed red squirrels to playbacks of conspecifics to trick them into thinking they lived in a high-density environment. And for each squirrel, we measured their fecal cortisol metabolites, or their stress levels. So here we have 9 observations for control squirrels and 9 observations for experimental squirrels. Now, if you recall, we analyzed these data as a 2-sample t-test, where we calculated the difference between sample means as 39.6 nanograms per gram and this resulted in an observed t-test statistic of 2.37. So we know that when our data are normally distributed and the variances are equal and the null hypothesis is true, then we'll get a sampling distribution of t-values that looks something like this. And based on this theoretical distribution, then, we can calculate that our p-value in this case is 0.03. Okay? But what if we violate this assumption of normality or equality of variances? Then this theoretical distribution might no longer apply. But that doesn't mean that we still can't calculate a p-value. Instead of relying on this theoretical sampling distribution, what if we create our own sampling distribution? We do this by permuting the data. So here we have the original data. Now, in this case, our null hypothesis is that there's no difference between the means. And if this is true, then we should be able to reshuffle our labels of control and experimental, and it wouldn't have any effect on our conclusions. So that's what I mean by breaking the hypothesized association. We hypothesize in our alternate hypothesis that this control population is different from our experimental population. And so if we break the association between the treatment and the fecal cortisol metabolites by reshuffling these treatment assignments, then that can create a null distribution of differences between our control and our experimental squirrels. So here I've used some R code, in particular the sample function, to permute the treatment labels here. This just randomly reshuffles these treatment labels, and you can see that the fecal cortisol metabolite values have remained the same as they were in the original data. What's changed is that we've randomly reshuffled the treatments associated with each of those fecal cortisol metabolites. Now, this is just one permutation of the data, but if we do this many, many, many times, and for each permutation, calculate the difference between sample means, we get a distribution of differences when the null hypothesis is true, meaning when we've broken apart this association between our treatment and our fecal cortisol metabolites, that looks something like this. Now, this is an empirical distribution. This is what we get when we do this many, many, many times randomly. It doesn't assume any particular underlying distribution. And so we can't calculate our p-value from a statistical table. Instead, we simply calculate our p-value as the number of permutations that are as extreme or more extreme than our observed difference from our original sample, either in the positive direction or the negative direction. And we can calculate then from this permutation test that the p-value is 0.0323. So this permutation test still assumes that our sample is a random representation of the populations, and it also assumes that our two populations have the same distributed data, whether they're normal or some other distribution. But beyond that, the permutation test doesn't rely on any particular underlying distribution. Instead, it creates an empirical distribution. And so this approach allows us to free ourselves of some of the assumptions of these underlying distributions and calculate our p-values using the power of computing to be able to calculate 10,000 differences in a reasonably short period of time. Now, when our sample sizes are low, these sorts of permutation tests can actually be a little bit less powerful than a regular parametric test. But when the sample size is large, permutation tests are actually just as powerful as our parametric statistical tests. So in summary then, statistics always involve some component of estimation and some component of inference. Some of the assumptions of our statistical tests are relevant for the estimation part of our statistical procedure, and some of the assumptions are about our inference. Known distributions only work for us to be able to make appropriate inferences and calculate our p-values if our data meet the assumptions of the underlying distributions that we use to calculate those p-values. Now, luckily, we can use distributions based on a normal distribution in many cases because most variables are normally distributed, and many sampling distributions of non-normal data actually become normal because of the central limit theorem, as long as our sample size is large. In situations where the assumptions of our statistical tests are not met, we can use non-parametric statistics because they often have fewer assumptions, but unfortunately these non-parametric tests are less powerful than their parametric counterparts. Finally, permutation tests allow us to use computing power to generate empirical null distributions and calculate p-values without assuming any underlying theoretical distribution.